Hello everyone, and welcome to this RUS Copernicus webinar on snow cover mapping with Sentinel-3 products. Today's case study will focus on mapping the snow cover extent evolution in the Sierra Nevada, California from February to May 2021. My name is Simon Boitard, and I work as a remote sensing engineer at Novartis in Toulouse, France. Today's webinar will begin with a short introduction to the RUS service. Then I will present the Sentinel-3 mission and associated products. After that, we will move on to today's exercise on snow cover mapping, and we will wrap up the session with a question and answer session. Total duration of this webinar should be about an hour and a half. And I would also like to highlight that this webinar is being recorded and will be available soon on our YouTube channel and our training portal. If you have any question during this webinar, I invite you to write them down on the WebEx chat, and I will reply to them at the end of the webinar. So let's start with the introduction to the RUS service. RUS stands for Research and User Support for Sentinel Core Products. The service is funded by the European Commission and managed by the European Space Agency. RUS provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines to handle and process data acquired by the Copernicus Sentinel satellites constellation. RUS also has a dedicated and specialized remote sensing help desk team, which translates your request into technical solutions. They will also provide with technical, thematical, and scientific support to help you handle and process the Sentinel data. We also have a wide offer of training activities such as webinars, face-to-face events, or online classrooms. The RUS service is accessible through two main interfaces. First, the rus-copernicus.eu web portal is where you will be able to register to RUS and apply for a VM to replay a webinar, for example. The rus-training.eu web portal is where you will find all the information about the upcoming webinars and face-to-face training events. RUS Copernicus also has a YouTube channel. So the service has been operational for more than 3 years now, and we have hosted more than 55 webinars. You will find all the webinar videos on our YouTube channel. So I highly advise you to visit the RUS Copernicus training YouTube channel, as I am sure that you will find additional webinars that are of interest for your work or your studies. Now let's move on to the Sentinel-3 presentation and the introduction to the Alchi products. Sentinel-3 was developed to fulfill several goals. So mapping and monitoring our Earth, ocean, and land surfaces, the Sentinel-3 mission provides a wealth of global data with a great accuracy on key environmental parameters, such as the ocean and land surface color, the sea and land surface temperature, the sea topography and sea level rise, and the measurements collected by Sentinel-3 are used as input data to the Copernicus Marine Environment Monitoring Service, or CMENS. This mission also ensures the service continuity between previous and future missions. So Sentinel-3 is a European Earth observation mission. It's a dual satellite mission carrying 3 distinct payloads, SRAL and MWR, which are dedicated to measuring the sea topography. SLSTR is the sea and land surface temperature radiometer. Alchi is the ocean and land color instrument. So as I was saying, Sentinel-3 is a dual satellite mission made up of 2 different platforms. Sentinel-3A launched in 2016 and Sentinel-3B launched in 2018. Both satellites are identical and are working as a pair to ensure better Earth surface coverage and time revisits. So now more information about the different Sentinel-3 payloads. Let's start with OLCI. OLCI is the Ocean and Land Color Instrument. It is an optical sensor, so basically a space camera, which measures the solar radiation reflected by the Earth. So it collects measurements only during daytime. It has a medium ground spatial resolution of 300 meters in 21 spectral bands. The width of the swath is of 1270 kilometers. The revisit time is less than 2 days at the equator when two satellites are operational. The main objective of this sensor is to screen the ocean and land surfaces to harvest biological information on our marine environment, such as algal blooms, fishing, or sediments. It's also used to monitor the land surfaces, such as the vegetation health, the snow and ice cover, and the data are also ingested in atmospheric studies, such as aerosol or cloud detection. The second payload is SLSTR, which is a dual scan temperature radiometer. So it has two different view angles for improved atmospheric corrections. This sensor has different channels in the visible and shortwave infrared part of the spectrum with a ground resolution of half a kilometer. It has additional channels in the thermal infrared part of the spectrum with a ground resolution of a kilometer. The main purpose of this sensor is to provide reference sea surface temperature, or SST, from space at a 1 kilometer ground resolution. It's also used for active fire detection. The last payload is made up of two instruments, SRAL and MWR. SRAL is the Sentinel radar altimeter, and MWR is the microwave radiometer, which quantifies the water content in the atmosphere. Working together, these instruments will be used to measure several parameters, such as the sea level anomaly, the sea surface height, or the significant wave height. In this webinar, we are going to focus on the use of OLCI products for snow cover mapping. So I'm now going to give you more details about the OLCI products, so the measurements acquired by OLCI. The OLCI products are available in two different resolutions. So the full resolution, FR, of 300 meters, and the reduced resolution, RR, of 1.2 kilometers. Then two levels of product are freely available to the users. First, the level 1B products contain the ortho-geolocated top of atmosphere upwelling radiances for the 21 spectral bands spatially resampled onto an evenly spaced cross-track grid. Those products also contain annotations on the illumination and observation geometry, as well as meteorological data such as wind speed, atmospheric temperature profile, and quality and classification flags to give contextual elements around the measure, such as whether the measurements was collected over land or over the ocean, where are the coastlines, if we are in a tidal region, if the pixel was affected by sun glint or if one of the spectral channel was saturated when collecting the measurement. Then those top of atmosphere upwelling radiances will be ingested by the on-ground level 2 processing chain. So two different processing chains, one dedicated to processing the measurements over ocean and the other dedicated to processing the measurements over the land surfaces. So the level 2 products that are output by the water processing chain contain the water-leaving reflectances for 16 spectral bands. You will also find key ocean color parameters such as the chlorophyll and total suspended matter concentration and their errors. And again, quality and classification flags. In the level 2 land products that are output by the level 2 land processing chain, you will find key vegetation indexes, integrated water vapor along an atmospheric profile, and quality and classification flags. In this webinar, we will use the OLCI Level 1B product in order to map the snow cover extent. So as I was saying earlier, OLCI has 21 spectral bands. So in the Level 1B products, you will find the radiances collected by these 21 spectral channels. These channels span the whole visible spectrum and a portion of the near-infrared spectrum. This table gives you the central wavelength of each channel as well as their function. I also have highlighted a set of 3 channels that are commonly used to generate a red, green, and blue visualization of our product. So we will use these channels later in the webinar. I will also show you how to generate another RGB view using a different combination of OLCI channels. Also keep in mind that in the native Level 1B OLCI product, you will find the radiances collected by the 21 spectral channels. So the radians are directly measured by OLCI and are the amount of light at the top of the atmosphere. During the webinar, we will need to convert those radiances into reflectances. What is a reflectance? It's the percentage of the amount of light leaving a target to the amount of light arriving to a target. Another important aspect about the OLCI products is their timeliness. First, the near real-time products are released to the users. Those near real-time products are mostly intended for users who need a quick access to the data, such as forecasting systems. They're available within 3 hours after sensing, but they may be incomplete and may not have the full data quality. The product we are going to work with today are the offline products. They are intended for most data users. They are available within a few days after acquisition, and the measurements are gathered by a granular length of 3 minutes for full resolution products and 1 pole-to-pole half orbit for reduced resolution product. Last available timeliness is the reprocessing timeliness. For this one, no time constraint, and the reprocessing of Sentinel-3 products will be performed whenever necessary. What does it mean? It means that currently, some new algorithms are being investigated by the space agencies or some improvements are being developed. Once those ameliorations or improvements or new algorithms have been developed, tested, and implemented, they're being incorporated to the operational processing chain, and then all the future OLCI measurements will be processed with the new algorithm. In order to have consistent time series, the agencies may decide to reprocess all previous OLCI measurements with the new algorithm and release reprocessed product collections. The OLCI products are distributed in a standard archive format for Europe, or the SAFE format. Basically, the OLCI products are distributed in a folder containing a collection of files. The measurement and annotation are stored in netcdf files, and there is a manifest file that explains the content of the package. This will become clearer to you once we actually start to open an OLCI product within the Snap software. A very practical aspect with Sentinel-3 products is their naming convention. Sentinel-3 products have very long name, but they contain a wealth of information about the data which is inside the product. So by only looking at a Sentinel-3 product name, you can know what's within the products without even downloading or opening the product. So here is a classical Sentinel-3 product name example. The first 3 digits give you information on the mission name. So S3A for Sentinel-3A or S3B for Sentinel-3B in our case. Then come the instrument ID, OL for OLCI, SL for SLSTR, SR for SRAL. You will then find the processing level 1 or 2. Then the data type ID. So EFR for top of atmosphere radiances, full resolution, but other data type ID exist, such as WFR or WST. Then come a set of two dates that describe the start and end time of the granule in UTC time. So in our example, this Alchi product was acquired on the 20th of June 2018 between 1 p.m. 58 minutes 49 seconds and 2 p.m. 1 minute and 49 seconds. Then in pink comes the time of processing of the granule in UTC time. So as you can see here, this product was processed approximately a day after its acquisition. So how are Alchi products disseminated to the users? So first of all, there is a free access policy to all Sentinel-3 level 1 and level 2 products. Then remember that there are two different on-ground processing chains, one dedicated to producing products over open ocean and one dedicated to producing products over the land and coastal areas. The open ocean products are distributed by EUMETSAT on the CODA data hub. This data hub has a rolling archive over a year. Products older than a year are then moved to the archive.eumetsat.int data hub. The reprocessed product collections will be distributed on the codarep.eumetsat.int data hub. If you have a request on Alchi marine products, you may contact ops@eumetsat.int. And before using CODA and downloading Sentinel-3 products from the CODA data hub, I highly advise you to read the CODA user guide. Then the products acquired over land and coastal areas are distributed by the European Space Agency on the Sci-Hub data hub. There, the products are kept online for a couple of months. Then they are moved offline and need to be asked back online before being available for retrieval. I also provided you with a link to the Sci-Hub user guide. So later in the webinar, I'm going to show you how to use the Sci-Hub in order to download Alchi products. So if you are new to the Sentinel-3 mission and the Alchi products, I also highly recommend you to read the user and technical guides that are available online. There you will find many useful information about how the measures were acquired, how to read the products, how to handle it, how to interpret what you're seeing. So those are really useful resources on how to work with the remote sensing data acquired by the Sentinel-3 mission. So now that everyone has a little bit of background on the Sentinel-3 mission and associated Alchi products, we're going to move on to our exercise. So today's case study will demonstrate a simple and powerful way of mapping snow cover with Sentinel-3 Alchi instrument between February and May 2021 over the Sierra Nevada and Eastern California. We'll process the Alchi products in the SNAP software. So for those of you who are not familiar with SNAP, SNAP stands for the Sentinel Application Platform. It is a free open source common architecture for all Sentinel toolboxes to read, process, and visualize the Sentinel-1, 2, and 3 products. You will find extensive documentation, tutorials, links to product, use cases, and help desk at the following link. Also, SNAP has been operational for several years now, and there is a very active user community on the STEP forum. So if you meet an issue or if you have a question while using the SNAP software or while processing Sentinel-3 data in the SNAP software, I highly advise you to visit the STEP forum, as there is a solid chance that another user before you has stumbled upon the same issue as you, and there's probably already an existing thread replying to your interrogation. Also, on this forum, the SNAP developers are very active and usually reply to any inquiries within a couple of days. So The STEP forum is an extremely useful resource when working with the Snap software. If you're also interested in broadening your knowledge about land applications using Sentinel data, you can watch our land monitoring with Sentinel-3 YouTube webinar, Land 04. And you can also watch our snow cover mapping with Sentinel-2 products called CRYO05, also available on our YouTube channel. So today we will map the snow cover extent evolution in the Sierra Nevada in California between February and May 2021. So we'll map the snow cover extent evolution for the area that's within the red square here. Before moving on to the practical part of this webinar, I'm just going to give you some background elements on snow cover mapping and why it is fundamental to monitor this variable. So snow cover is the land area blanketed in snow at a given time. Air temperature is one of the main factors that determines the amount of precipitation that falls on land as snow and its melting rate. In many regions of the world, warming trends are inducing fewer snowfalls and earlier snow melt. While snow cover in winter has remained fairly steady and has increased in the fall since 1972 in North America, the United States Environmental Protection Agency, EPA, has found that spring and summer snow cover have been plummeting. In fact, the US snow season has shortened by more than 2 weeks in roughly 50 years. The last day of snow now being 19 days earlier than it was in 1972. In particular, climate change has made California drier and hotter, which means that more rain than snow is now falling. Since much of the rainfall evaporates, spring and summer snowpack constitutes the main water source to fill up reservoirs that fuel human activities such as agriculture or hydropower generation. The decreasing snow cover and the shift in snow season are contributing factors to the mega drought California has been experiencing since the year 2000. These past 22 years have been the driest years in at least 1,200 years based on tree ring records. And this has now major impacts on human lives and food production in this American state. For the first time, the federal government is thinking about cutting water supplies by 25%. Hence, monitoring snow cover is of prime importance to determine the amount of available water in California. So snow cover can be characterized through several variables. The snow cover area that we're going to look at today, but you can also monitor the fractional snow cover, the snow water equivalent, the snow depth, the albedo, or the liquid water content. It's of course possible to monitor the snow cover with ground observations, but very often the snow-covered areas are remote regions where it is difficult to set up in situ measurement means. Moreover, the in situ measurement techniques usually cover a limited area and do not allow to monitor a wider regions. That's why, with their high spatial and temporal resolution and coverage, Earth observation satellites constitute key tools to assess the snow cover on a regular basis. So several remote sensing snow cover products already exist. They either offer a global coverage at a limited resolution or a regional coverage at higher resolution. If you're interested in monitoring snow cover with existing Earth observation products, I highly advise you to visit the THEA web portal and have a look at their snow products. The NSIDC website is a reference for monitoring snow cover in the Northern Hemisphere, and also the Copernicus Land Monitoring Service offers very useful and reliable products to monitor the cryosphere. In today's webinar, we are going to compute the normalized difference snow index, or NDSI, from the data collected by the ocean and land color instrument. The NDSI is related to the presence of snow in a pixel and allows to distinguish snow from most cloud types. Indeed, on satellite images, snow may appear as bright as clouds. In the shortwave infrared part of the spectrum, snow strongly absorbs solar radiation as opposed to clouds. As Olchi has no Swier band, Kokanowski et al., and I provided you with the link to the paper, have adapted the index computation for this sensor. So NDSI is a remote sensing index that uses the combination of two Olchi channels, the channel 17 and the channel 21. But be careful here, because to compute the NDSI, we need the atmospherically corrected reflectances. And remember, in the Olchi level 1b products, we only find the top of atmosphere radiances. So we'll need to convert those radiances into reflectances and correct them from the atmospheric effects. An NDSI value greater than 0 indicates the presence of snow, while an NDSI value lower than 0 indicates that the pixel is free of snow. Now we're going to move on to the practical part of this webinar. First, I'm going to show you how to download Sentinel-3 data from the Sci-Hub. It will be followed by a short introduction to the Snap software, and then we'll actually process and analyze Olchi Level 1b products. We'll start with exploring the products, then we'll build a processing graph, and I will show you how to process Olchi data simultaneously. We'll operate a collocation between the various products, and we'll end up doing a classification. Then we will have a little discussion about our results, and I will show you some extra steps, such as importing our results into a GIS software. So the practical part of this webinar will be carried on a RUS virtual machine. So here I'm already connected to my RUS virtual machine. So this is the RUS desktop, a classical RUS desktop. When replaying a webinar on a RUS virtual machine, you will find the webinar training kit in the training folder. Today's webinar will be called CRYO05, 05, Snow Cover California S3. A RUS training kit is organized in 3 different folders and has a PDF tutorial that describes all the processing steps. In Ox data, you will find auxiliary data that we will use during this webinar. Original is where the input data that you will download should be stored. And then processing is where we will store the results of our processing. So let's start with the Olchi data download. So in this step, we are going to download the Sentinel-3 scenes that are used for this exercise from the Copernicus Access Hub. So as I told you, we're going to map the snow cover extent in the Sierra Nevada, California from February to May 2021. So here we are going to download one Sentinel-3 Olchi Level 1b product per month, meaning that we are going to work with 4 different input products, one acquired on February, one acquired on March, one in May, and one in April. And ahead of this webinar, I selected low to no cloud coverage products so that we are able to have the most accurate snow cover mapping. So to access the Copernicus Open Access Hub, you can access it from any web browser and go to the sci-hub.copernicus.eu web portal. The Sentinel-3 data are distributed on the Open Hub. So click on the Open Hub. So all Sentinel products are freely available to the users, but in order to download them, you still need an account. If you do not have an account, hit the Sign Up button. Here I already have an account, so I directly log in. First thing we need to do is to drag the map to our area of interest, here, Eastern California. Then using the center wheel of our mouse, we can zoom in a little bit more to our area of interest, located eastern of San Francisco and southern east of Carson City. Selecting this button here will allow you to draw an area of interest. Then you can select additional search criteria by hitting the 3 horizontal bar button here. So here I'm going to show you how you can download the product that was acquired on February. Set the sensing start time to February the 6th, 2021, and the sensing stop time to February the 6th, 2021. So we're interested here only in products acquired on the 6th of February, 2021, because this is a cloud-free day. Then if you go lower in the list, you can select the Sentinel-3 Mission. Here we'll work with a Sentinel-3A product. If you're interested in both mission, you can leave this criteria blank, but here Sentinel-3A. Here, many product type available to the users. But as you know, we are going to work with the OLCI level 1B product full resolution. In the instrument section, you can select the instrument you're interested in. Here, it's not mandatory as OLCI is already precised with the OL ID here, so we can leave it blank. You can also specify the product level. Here, it's again not mandatory because the one is already tells the product level. But for example, you could be interested in downloading all Sentinel-3 level 1 product and just specify this criteria. Okay. Once everything is set up, you can hit the search button. The search gives us one result, one tile covering our area of interest. And you can see the geographical hold of the product in blue. What's very practical with the Sci-Hub is that you can check the product before downloading it. So here you can see that the image acquired by Sentinel-3A OLCI instrument is relatively free of cloud on that day. And then once you want to download the product, you just need to hit the little arrow here. Normally this product should be offline, but I requested it to be back online before the webinar. So here, hitting this button will trigger the download. And if you hit OK, it will start to download the product. The 3 other products that we're going to use are one product acquired on March the 5th. Here, hit the search button. Here, again, cloud-free Sentinel-3 image. The next one will be acquired on April 1st. Search button. Here you can see that the product appears offline. If you want to request it back online, hit the little arrow here and it should trigger the offline product retrieval initiated. If you have an error message, just close the window and ask it again to be back online. Then when you visit your cart here, you can see that the product has been added to your cart and the request is currently running and it will be back online in a few hours. And the last product that we will use was acquired on May the 6th. So here I'm not actually downloading the product in order to save time during this demonstration. But when replaying the webinar, you will need to download the 4 products. So on a RUS virtual machine, the products will be downloaded in your home RUS folder as a zip archive. Then you just need to move these products from the RUS folder to the shared training CRYO05 original and unzip the archive using the Open with X Archiver option. Once this is done, you can open the Snap software by double-clicking on its desktop icon. So here the Snap software open. No products have been ingested yet, so we'll start with ingesting our first product. You can do it by hitting this button here, Open Product, or from the File Open Product option. Then you just need to navigate to Original and to your product of interest. So here, let's start by opening the first product that was acquired on February the 6th. Here you can see that the radiances and auxiliary data are stored in NetCDF files, and there is the manifest file here, XML, that explains the content of the product, and this is this file that we're going to use to open the product within Snap. So select the XML file and hit Open. You can see that now there is one product in the Product Explorer tab, and you can expand the product tree by hitting the key button located left of the product. So you can unfold the product content and appreciate how Snap conveniently gathers the data into several folders. The main data of interest, so the top of atmosphere radiances in the 21 spectral bands of Volchi, is stored in the bands OA radiance folder. So see the radiance collected by Volchi in the 21 spectral bands. The other folders contain data that give additional information on the context of the measurements. For example, the masks folder encloses very useful information on the quality of the retrieval, such as, for example, quality flags land, telling you if a pixel is located on land or not. Metadata contains static information about the product, such as the timestamp, the platform name, the observation mode, etc. If you want to check the properties of a band, right-click on the band of interest and hit Properties. Here, you will find the name of the band, a more detailed description, the unit of the variable. Okay, so now that we have ingested a product in the Product Explorer, we would like to generate a view of our product. To do so, right-click on the product and select Open RGB Image window. So we're going to create a classical RGB image, selecting the 8th channel for red, the 6th channel for green, and the 4th channel for blue. Hit OK. And the view automatically opens in Snap. So when you are on the view, you can select the hand button here in order to move on the product. And you can zoom in by using the center wheel of your mouse. Here. Then drag the products to our area of interest. In the World View tab, you can move the globe and see where on Earth your product is located. So this gives us a similar view as the Sci-Hub. So on the generated view, you can notice that most of the Sierra Nevada mountain chain is covered in snow on February 6th, 2021. In order to enhance the snow visualization, we're going to open a second view with different Olchi bands. So again, by right-clicking on the product, select Open RGB Image window. And this time in the Profile section, choose the Olchi 1763 profile and hit OK. In order to compare both views and visualize them simultaneously, go to Window, Tile horizontally. Then, if you want to have a simultaneous navigation in between both views, in the Navigation tab here, make sure to have those two buttons selected. This will synchronize views across multiple image windows, and it will also synchronize the cursor positions across multiple image windows. This way, when moving on one view, you also move on the second one. You can zoom in, and you can see how this view allows a better differentiation between snow-covered area and other land types. Okay, so now we can close the RGB view opened with the natural colors. Let's now open the 3 remaining all-chip products. So another way of opening a product within Snap is from a file browser, navigating to your product, and drag and drop the xfdu manifest.xml file. So here I will open the product in chronological order. So the product from March, the product from April, and the product acquired on May. We're going to generate an RGB view for each of our products using the 17.6.3 profile. So March, April, and May. Again, to simultaneously explore the 4 months, go to Window, Tile horizontally. And then by zooming in, we can visually assess the rapid snow cover decrease from February to May in the Sierra Nevada, California. So visual inspection of the products clearly shows a strong snow cover decrease over the course of spring 2021. So to more quantitatively assess the snow cover extent, we will compute the so-called Normalized Difference Snow Index, or NDSI, that I introduced to you earlier. And remember, to compute this NDSI, we need atmospherically corrected reflectance. But in our native all-chip level 1B product, we only find top of atmosphere upwelling radiances. So our first pre-processing step will consist in using the optical pre-processing Rayleigh correction module of Snap. So at the time of writing this exercise, this module does not work in batch mode, and we need to apply it to each individual scene one by one. The Rayleigh correction module fully corrects the selected bands for molecular absorption and scattering to compute the so-called bottom of Rayleigh reflectances, or RBRR bands. This module does not account for aerosol absorption and scattering, so these effects will be neglected in our study. So here we're going to first apply the Rayleigh correction module to the Sentinel-3A product from February the 6th. So in the input-output parameters tab, make sure that the source product is set to the product acquired on February the 6th. Leave the default target product name, can save as BIM-DMAP, which is the default Snap data format. Set the directory to processing Rayleigh, select, and in the processing parameter, we will compute the bottom of Rayleigh reflectances for 082, 3, 6, 17, 2, 3, 6, 17, and 21. To select multiple bands simultaneously, maintain the Control key button from your keyboard. Make sure that only the bottom of Rayleigh reflectance bands option is selected. Finally, you just need to hit Run. So the processing may take up to 10 minutes per all-chip product. So I have done this preprocessing step ahead of this demonstration, and you need to repeat the operation for each of the four Sentinel-3 level 1B all-chip products. So once this is done, we can close the 4 RGB views here, and we can also close the 4 original all-chip level 1B products. So after the Rayleigh correction is applied on each original all-chip level 1B products, they will automatically open in Snap. Here I need to open them one by one. So the Rayleigh corrected product from February, March, April, and May. So here you can see that the products were saved in the BIM DMAP format. And so to open a BIM DMAP format in Snap, just drag and drop the .dim file in the Product Explorer tab. Okay. So now that we have computed the bottom of Rayleigh reflectances for the 4 products, we're going to apply the following processing steps. First, we'll perform a spatial subset to crop the products to our region of interest. Then we'll compute the NDSI and the snow flag. We'll reproject our products to set a coordinate reference system, or CRS, to our products, and we'll collocate the 4 products to stack the snow flags for the individual month all together. So repeating the analysis for every image one by one would be very time consuming. For this reason, we can create a graph containing all steps of our methodology and use the batch processing option of Snap to run bulk processing. So to create our preprocessing graph, we'll use the Graph Builder tool to create a chain with the processing steps we want to apply, and at the end, only the final product will be physically saved. To create an empty graph, go to Tool, Graph Builder, and at the creation, the graph only has 2 operators, read and write. To avoid any confusion, right-click on the write operator and delete it. In the Graph Builder, we will not define any parameters in the tab. We will only create and save the graph. So first, we need to create a subset of the image. So to add a block in the Graph Builder, right-click anywhere, then Add, Raster, Geometric, Subset. And you see that when we add a block, a tab appears down there. Then connect the read operator to the subset block. To connect 2 blocks, start from the right of the input block to create a red arrow and drag it to the following block. Now our 2 blocks are connected. Then we'll compute the NDSI and the snow flag. For this, we'll use the bandmath operator. So add, raster, bandmath, and connect. Then we'll reproject our products, add, raster, geometric, reproject, connect the blocks. And finally, we want to write output products to save it. So add, input, output, write, then connect. So finally, we will save our empty graph. And you may also notice that there is a warning message here. This is normal as we have created an empty graph and we have not set any parameters yet. So it's just telling us that the expression defined in the bandmath operator is invalid. This is normal. We have no expression so far. So save your graph by hitting the Save button and save it in the OxData folder and name it ndsi.xml. Save it. Okay, so now we have created an empty processing graph, but now we need to tune it and execute it. So if this, you can close the graph builder. So if the same processing scheme is applied to multiple images, the batch processing tool is what you are looking for. So to use the batch processing tool, go to Tools, Batch Processing. First, you need to load the graph we want to run. So hit the Load Graph button and load the NDSI graph we just created. The tabs corresponding to each block appear here. In the Input-Output Parameters tab, unselect the Keep Source Product Name option. In the same tab, we will add all opened products, so all the Rayleigh corrected products from the Product Explorer window by hitting the Add Opened button at the right. So all 4 products from February, March, April, and May are now taken into account as inputs for our batch processing. You can also add external products by hitting the Add button here and navigating to a product. Okay, now let's move on to the subset tab. So in the subset operator, 2 kinds of subsets are possible. Band subsets, because as you saw, not all chi bands are useful for our study. Here we have already restricted the number of bands when performing the Rayleigh correction. So just select all bands. To select all bands, use the Ctrl-A keyboard shortcut. Here we'll mainly perform a geographic subset. So select the geographic coordinates option and we'll subset our area of interest to the following polygon. So if you go down a little bit, you'll find here a bar where you can define your area of interest. So here we'll use this polygon. And if you hit update, you see a little yellow rectangle appearing here. And if you want to zoom in to your area of interest, you can hit this button. So here it's a well-known text defining the corners of our area of interest. So longitude and latitude of each corners. And the first corner is repeated twice so that we are sure that the square is closed. Once this is done, we can move to the band math operator. So here we'll compute a band called snow flag. So in the target band option, write snow flag. Set the no data value to not a number, because if you let it to 0, the no data value may be confused with an NDSI actually set to 0. And in the Edit Expression tab button, we can define our bandmath expression. Here we will use the following expression. What does this expression mean? It means that if the NDSI, so this is the NDSI here, the index computed with the combination of channel 17th and channel 21 from Olchi with the bottom of Rayleigh reflectances. If the NDSI is greater than 0.03 and the bottom of Rayleigh reflectance of channel 2 is greater than 0.4 and the quality flags land is true, so if the pixel is located on land, then we will set our snow flag to true. Otherwise, the snow flag will be set to false. So this expression and the associated thresholds values come from the Kokonowski and all paper. Then hit OK. You can see that here there is no error in our expression. Also, if you want to write a different expression, you can find all the bands and flags name that are available. Okay, this is how you know the correct names to put in this tab. So hit OK. After that, let's go to the Reproject tab. So we will define a custom CRS. So choose the UTM WGS84 automatic towards the bottom of the list and unselect Reproject type point grids. Finally, in the right tab under the name, keep the default name. It's basically the input product name with the name of the processing step that we're going to apply, projected, subset, Rayleigh, and bandmath. Be sure that the directory is set to processing. And after that, you just need to hit run. And this will trigger the automatic processing of the 4 Rayleigh corrected Olchi products. So this step may take up to 5 minutes. I'm not going to execute it during this demonstration. But once this is done, you can close the batch processing window, and all the output products should automatically open in Snap. So here I need to actually import them. So process product from February, March, April, and May. And so by expanding each product in the bands folder, you can see that now our products contain a single band called the snow flag. So you can open the 4 snow flags from February to May 2021. And if you want to visualize it simultaneously, tile horizontally. Okay, so you can see actually the snow flag for each month. February, March, April, and May. And again, it allows you to assess the rapid decrease of the snow cover extent between February and May 2021. So you can notice that all products have effectively been cropped to our area of interest and have also been reprojected. And the areas blanketed in snow appear in white as opposed to snow-free areas in black. So before moving on to the collocation step, I would just like to show you how you can check the accuracy of the computed snow flag, because here we see that, okay, indeed a snow flag has been computed, but we don't know how accurate it is compared to the visual, the RGB views that we generated earlier. So if you want to check the accuracy of the computed snow flag by visual inspection, for this, so you can close the 4 snow flag views. So for this, we're going to open an RGB view of the Rayleigh corrected product. So right-click on the Rayleigh corrected product from February the 6th, for example, and hit Open RGB image window. Here, select channel 17 for red, 6 for green, and 3 for blue. So when you open this RGB view, you can notice that the generated image has a white veil on it. So this is due to the settings in the color manipulation tab here. So in this tab, for each color component, hit the stretch histogram horizontally button and then define the min and max slider to 0 and 0.6. To change a slider value, double click on its value and just change the value and press enter. So define it between 0 and 0.6 for each view, each color component. 0, 0.6, blue, 0, 0.6. Okay, this didn't work correctly here. Make sure 0. Okay, so now our view looks way better and similar to the one we generated earlier. Now on this product, we're going to compute the snow flag again. So right click on the product and select band math. So again, define the target band name to snow flag and make sure that the virtual save expression only, don't store data option is selected. On the edit expression button, we'll use the same snow flag expression as we have used. Then hit OK. And finally, hit OK here. So the snow flag band automatically opens in Snap. Now we can go to View, Tool Windows, Mask Manager. So here, this tool displays all the available masks in the product. So these are the masks that I was telling you earlier. So let's go back to the RGB view. For example, if you activate the quality flags land that we have used to generate our snow flag, you can see that there is a mask displaying on all land surfaces. It's the same with the fresh inland waters, for example. Same with the coastline, etc. You can change the color of a mask or set its transparency. For example, here, setting the transparency to 0 completely masks out the land surfaces. Okay. So now we are going to create a snow mask out of our snow flag band. For this, hit the little FX button here. It works a little bit like band math. So here you can show the bands, and we will define our new mask with the following expression: snow flag equals 1. Hit OK. The new mask is automatically created at the bottom of the list. Let's call it snow flag and set its color to cyan. Sorry, not snow flag, but snow mask. Here it didn't work with snow flag because there's already a band called snow flag. So call it snow mask and change the color to cyan. Then if you move in on your area to your area of interest, if you zoom in, you can actually check the accuracy of the snow mask and the snow flag by activating and deactivating the mask. Now, if you want to tune our algorithm expression, go back to the Product Explorer, expand the product content, and on the snow flag band, right-click and hit Properties. By hitting this button next to the pixel value expression, you can play around with the expression and change the different thresholds. For example, let's try to set a threshold of 0.9 on the bottom of Rayleigh reflectance of channel 2 and hit OK. Here you can see that the mask automatically adjusts to this new value. And you can see that this threshold value is way too conservative. So this is how you can play around with the threshold and tune the different thresholds to have it best suited to your area of interest. Okay, so let's take it back to 0.4, but you could also set it to 0.3. Okay, for example, you see here that with 0.4, we're maybe a little too conservative and missing some areas that are lightly covered in snow. For example, if you set it to 0.3, if you're interested in encompassing more snow-covered area, it's more relaxed, okay? But here we'll stick to 0.4. Hit OK, and then you can hit close. Another very useful option when you have your snow mask is to go to Raster, Masks, Mask Area, then select your snow mask, hit OK, and you can see that 30,000 kilometers squared were covered in snow on February the 6th over the Sierra Nevada. Okay, so this is how you can tune and check the accuracy of your snow flag. Now let's study the snow cover time series. So after batch processing the products, we have 4 different processed products, each containing 1 snow flag band. So first you can close the views and you can also close the Rayleigh products. Close for products. Okay. So this step aims at stacking all the snow flag outputs of the batch processing in a single product to allow further processing. For this task, we will use the collocation tool, which enables the user to collocate spatially overlapping products. So collocating products implies that the pixel values of all slave products are resampled into the geographical raster of the master one. Here we will choose the product from February the 6th as the master, and the products from March, April, and May as slaves. So let's go to raster, geometric operation, collocation. For the master product, choose the process product from February the 6th, and for the slave products, add the product from March, April, and May here. Okay. You can also add external products, add product files. Name the output, collocate Feb, March, April, and May. Save as bin dmap in the processing directory. So the master bands will be renamed with their original name with a little m. So in our case, snowflag underscore m. For all slaves, we will have snowflag underscore s with the slave number ID. So 0 here for March, 1 for April, 2 for May. So this is why it's important to have the products open in chronological order. Otherwise, if it's not open in chronological order, you will have 0 for the first product in the list, 1 for the second product in the list, etc. The resampling method select the bilinear interpolation resampling, and finally, hit run. So after a few seconds, the collocate February, March, April, and May products should open in the Product Explorer tab. Okay, so you can close the collocation tool. You can expand the output product. And in the band, you see snowflag M for February, S0 for March, S1 for April, S2 for May. If you want, you can open the 4 snowflags, but they're pretty similar to what we had earlier. So now we are going to assess the snow cover decrease. So we're going to derive a single band out of the 4 snowflag bands to classify the pixels depending on when they were identified as snow covered. So I'm going to show you the class very quickly. So here we will have the class number 1 if the pixel is snow covered from February to May or in May only. The color will be white. Then 2 if the pixel is snow covered from February to April or in April only in cyan. 3 if the pixel is snow covered from February to March or in March only, dark blue. And 4 if the pixel is snow covered in February only, navy blue. So to compute this snow cover band, right click on the collocated product, hit band math. Name the band snow cover, unselect the virtual option this time, and in the band math expression, copy and paste the following expression and hit OK. So here again, what does it mean? If the 4 snow flags are set to true, or if only the snow flag from May is set to true, then 1. It means that the pixel was snow covered from February to May or in May only. Then if only the snow flag from February to April are set to true or only in April 2, then etc. for February and March and February only 3 and 4. Then hit OK. So a black and white view automatically opens in Snap. So to add a better color ramp, we'll use a color ramp predefined before this training session. Go to the Color Manipulation tab, open a color ramp from File, navigate to Aux Data, and select snowcover.cpd. Here hit no, and you can see our 4 classes here. So in navy blue, basically the snow that melted in February. In dark blue, the snow that melted in April. In cyan, the snow that melted in April, sorry, and in dark blue, the one that melted in March. And in in white, the remaining snow in May. So you can see how fast the snow melted over the course of spring. Here in the basic option, you only find one color tab. If you want to find all snap default color ramp again, navigate to the RUS folder here. Select the .snap file name, then navigate to aux data, color palette, and here you will find all the color palette. So here I already have the NDSI, if I'm not wrong. Or maybe not, sorry about this, but you can find all the default color palette here. So, okay. Again, we can also use the mask manager to create new masks. So here I have the X show bands. I'll define a new mask called, oops, I didn't call it snow cover, but snow VOER. Sorry for the mistake. Strictly greater than 0, meaning that the pixel is snow covered at a given time between February and May 2021. We can call it snow mask global, and we can compute its area from the raster mask area. So here you can see that approximately 28,000 kilometers squared were covered in snow in February, at least, or at any given time in between February and May 2021. Now, if you want to check which was the portion that was still snow covered in May, you can define another mask, show bands, call again, and here snow cover equals 4, which is our class number dedicated to the month of May. Hit OK. Sorry, it wasn't equals 4, but equals 1. So here, okay. So you can compute, so this is, we can call it snow mask May. From raster mask area, you can compute the area from snow mask May, hit OK. And you can see that in May, not even 10% of the area covered in snow in February was remaining. So 90% of the snow had melted. So this is a rapid decrease. And then the remaining snowpack in May is not sufficient to fuel all the water needs of California. Okay, and here with our new mask 2, it's snow mask melt February. You can see that in February only, so from February to March, if you compute the mask area, you can see that 12,000 kilometers of snow-covered area became free of snow between February and March. So this is almost 50% of the snow-covered areas. So this is a lot. Okay, so one last step, if you're interested in exporting your output to a GIS software, Snap has an option for this. You can make sure to have the collocate Feb, March, April, May product selected, then go to File, Export, and select the GeoTIFF format. So you can save it in the processing folder. In the subset tab, we do not want to do a spatial subset, only a band subset. We're only interested in exporting the snow cover band. Hit OK. Hit No. And finally, export product. Now that we have our GeoTIFF, we can open the QGIS software. From the XYZ tiles, load the OpenStreetMap in the Layers tab. And then we can simply processing drag and drop our TIFF here. It automatically opens in Snap as a in QGIS, sorry, as a black and white view. You can double click on the layer. In the symbology section for band rendering, select single band pseudo color. And here we are going to load a predefined color bar called snowcover_qgis.txt. Hit open, and here you hit OK. You can see the view of the snow cover extent evolution from February to May with a nice legend here. Okay, so this was the last step of this practical webinar. So now some concluding remarks before moving on to the question and answer session. So satellite imagery is widely used to map and assess snow cover extent, especially in remote areas. Spaceborne technologies offer a frequent and global coverage of our continents. As this exercise highlighted, simple index computations based on the spectral properties of snow in the near-infrared part of the spectrum allow a relatively easy assessment of the snow cover extent. The Sentinel-3 constellation constitutes a valuable asset to monitor the snow cover evolution at a large scale on a frequent basis. Furthermore, the all-chip products could be combined with other sensors to create multi-sensor products and hence ensure gap-free coverage of the Sierra Nevada. Here, we decided to work with only one product per month, but you could also have a more precise snow cover monitoring by downloading several products per month. For example, one product per week, if there is one cloud-free product per week. So in this exercise, we have used low no cloud coverage images. Even though NDSI allows to distinguish snow from most cloud types, Archie cannot see through clouds. So it remains challenging to accurately assess the snow cover extent from space under very cloudy conditions. Furthermore, Archie only acquires data during daytime. The observations are hence limited at higher or lower latitudes during the winter season when daytime is limited. This demonstration also does not take into account the forest coverage of the area. Indeed, when fresh snow falls, it first falls on trees. As the snow gets older and heavier, it falls off the tree branches and may be hidden from view. Some forest areas may be covered in snow, even though they do not directly appear as snow covered from space. So these could lead to an underestimation of the snow-covered area. If you want to learn more about this topic, you should watch our previous CRYO03 webinar. Finally, monitoring the snow cover area is one way of monitoring snow cover. One could also study the fractional snow cover, the snow water equivalent, the snow depth, or the liquid water content. If you want to replay this webinar after the session, the training kit will be available soon on our on the RUS Copernicus web portal. So you can simply go to rus-copernicus.eu, hit login register. If you do not have an account, create your Copernicus SSO account. Otherwise, hit login, and then from your RUS dashboard, your RUS service, your training activities, you can ask to replay a webinar. For example, here, CRYO03. Hit I have read and agree to the terms and conditions of the RUS service and request a webinar training. So I would like to thank you for your attention, and we're now going to move on to the question and answer session.